So good evening everyone. So this is extra session for the engineering hydrology live session. So in this session what we are going to do is we are going to summarize all the modules, and we are going to also revise few of the important numericals from each of the module. So in this module we'll start very first with the module 1. So in the first module we started with the introduction of the subject. So we started with uh, the definition of hydrology, then how water exists in different forms on the earth, that is gaseous, liquid and solid. Then we talked about the definition of hydrology. So hydrology is nothing but you just have to remember these three words, that is occurrence, distribution and circulation of water, right? Then we talked about hydrological cycle. Then hydrological cycle, uh, we talked about like it is a circulation of water between the earth and its different phases, like between the earth and atmosphere. Then we talked about very important term which is called as global water budget. So we talked about how water exists in different form, that is how it exists in oceans and seas, which is saline, which is 96.5%. Then how water is available on land, that is 3.5%, and which is further divided as 1.5% is saline, and only 2.5% of entire global water is fresh water, which is available to us to use in other different forms, like that we can use it. Then once we cover global water budget, we came with a very important definition of residence time. So residence time is nothing but the average time that the water is present in different phases. So the average time that the water is present in the global river is around 17 days. The water which is present in atmospheric water is for very short period of time, that is 8 days. And obviously we know the groundwater flow is very slow, so obviously it will take more time there. So the residence time for groundwater is 100 years for shallow and 10,000 years for deep water. Then we talked about what is catchment. So catchment is nothing but the boundary of your basin, right? So there are different words related to different names of catchment. We call it as watershed, right? We call it as basin, we call it as sub-basin. So it is nothing but the boundary, right? Then we talked about two important approaches. One is Lagrangian approach and another is Eulerian approach, right? So we have studied this in distinguished form. So in Lagrangian approach we use the control mass concept. So what does control mass mean? So control mass is nothing but we focus on the movement of the particle, right? And in Eulerian approach we use control volume. So in control volume what we do is we fix the frame of reference, and then we focus on the moving fluid which is entering that frame of reference, right? Then we talked about two important fluid properties, that is extensive property and intensive property. So intensive property are those properties that are independent of masses, and extensive properties are those properties that are dependent on mass. Then comes the very important theorem that we have studied in the very first module, that is Reynolds transfer theorem. And using this theorem we have further derived two important equations, that is continuity equation and momentum equation, right? So the important thing to remember about Reynolds theorem is it is based on Eulerian approach. So this can be asked like it is based on which approach. So it is based on Eulerian approach, right? Then the other thing to remember is these two parts, like what are the two parts of Reynolds transform theorem. So the first part is that the time rate of change of extensive property stored is within the control volume, and the net outflow of the extensive properties across the control surface. So the three important things that we remember is it is based on an Eulerian approach, and the first and second term we should remember. Then this is the standard equation of Reynolds transfer theorem. Using this equation we can derive conservation of mass, momentum and energy. So this is all about like what we have done in the introduction class of module 1. Then we started talking about atmospheric water, like how water is available in atmospheric water. So in atmospheric water we studied about three important hydrological processes, and those are precipitation. We studied about precipitation, we talked about evaporation, and we talked about evapotranspiration, right? So in the very first part of atmospheric water in this module we have covered few definitions, like the definition of vapor pressure, specific humidity, saturation vapor pressure, relative humidity and dew point. So we should remember all this definition. Either of them could be asked in numeric as an MCQ in the examination. Then we talked about how the precipitation is formed. So the precipitation is formed based on these two important concept. First is lifting of moist air mass and the second is nucleation, right? In lifting of moist air, we talked about like there are different types of lifting, right? That is, there are frontal lifting, there is orographic lifting, there is convective lifting. So we should remember, we should revise all those concepts also. Then we talked about what are the different forms of precipitation. So here we talked about how the form or different form of precipitation varies with the size of precipitation, right? So we talked about if according to the size of precipitation could be either drizzle or either rainfall, right? So it depends on the size of particle. Then how to measure the rainfall? So we could measure rainfall using rain gauges, and the rain gauges are of two types, that is non-recording rain gauges and recording gauges. So there are certain limitations with recording and non-recording gauges, and those limitations is it is an instrument which is located at a particular point, so it will give us point data. So if we want to cover a large area, we have to obviously go with remote sensing product. So there are radar based product or there are satellite based product, right? Then we talked about how we can represent the precipitation. So if you want to cover larger area, we can use isoetal maps, right? So isoetal maps are what? So we should remember the definition of isoetal. It is the line joining point of equal rainfall depth. So it is kind of a contour map for precipitation, right? Then we talked about temporal representation. So here we can use, the important thing is hydrograph, and we should remember what is hydrograph. Hydrograph is nothing but the graph between rainfall intensity and time, right? Then we talked about very important thing which we have also looked into numerical perspective also, like how to determine the optimal number of gauges that the data need to be checked for it, right? So here we talked about mass curve, double mass curve and mass curve method. Then we talked about few of the different methods for taking the average of aerial rainfall. So the important method here is Thiessen polygon method and isoetal method, right? So we have to revise the limitation of Thiessen also and the advantages of isoetal also. Then we talked about the another hydrological process which comes under this module of atmospheric water was evaporation, right? So what was evaporation? Evaporation is nothing but water changes to vapor state, right? It evaporates. The water evaporates at the free surface of liquid below the boiling point through the transfer of energy. So here the important thing is how we can measure or estimate evaporation. So there are different methods. The first method was experimental method. So we could use, we can take help of pan evaporator, and we can find the evaporation rate, and also we can use empirical equation or analytical method, right? So in the analytical equation we talked about three approaches, different methods. The first was energy balance method, which is obviously taking place due to heat energy. Then we talked about aerodynamic method, where the two important terms were humidity and wind velocity. And when we combine these two approaches, that is energy balance and aerodynamic method, we can use this together and we call it as combined approach, right? Then the another variable, important hydrological variable, was evapotranspiration, right? So what was evapotranspiration? It comprises of two different processes, that is evaporation and that another one was transpiration. So when we combine these two approach variable, we get evapotranspiration. So we know what is evaporation. It is the loss of water from water body, right? And transpiration is nothing but loss of water from plants. Then we talked about different types of evapotranspiration, that is potential, actual and reference crop evapotranspiration. Then we talked about how we can estimate evapotranspiration. So again we talked about lysimeter, which is one of the instrument that is used to measure evapotranspiration. So we have covered how it is working. So it is nothing but a watertight tank in which we add water by weight, or we add water by in terms of volume, and we measure like how much amount of water is lost or water is used, and that will give us the evapotranspiration rate. Another methods were empirical equation. So we talked about Thornwitt equation, Blaney-Criddle equation, and there are theoretical equations like Penman equation and PM equation. So we have seen numerical in each one of them. Then we came to third module, right? So in third module we talked about subsurface water, right? So here we understood the phenomena of like important terms, like first we talked about few important properties of soil, like porosity, void ratio. Then we talked about how the porosity keeps on changing with respect to depth, right? Then we talked about one of the important equation like of 1D unsteady unsaturated flow equation known as Richards equation. So we have seen the derivation of Richards equation also, and we have seen this how the moisture content varies with respect to depth in subsurface zone. Then we have seen the relationship between infiltration rate, cumulative infiltration and infiltration capacity, and we have derived relationship between infiltration rate and cumulative infiltration. So if we have cumulative infiltration, we can integrate, we can take derivative of it and we can get infiltration rate, and vice versa. If we have infiltration rate, we can integrate it and we can get cumulative infiltration. So we have seen this relationship between each of them. Then we talked about how we can measure infiltration, right? So we have studied empirical equations, like there were many empirical equations like Kostiakis equation, Horton's equation, and we talked about theoretical equations such as Green-Empt equation and Philip equation. So we have seen numerical on each of them. Then we talked about very important concept of ponding time. So what was ponding time? Like sufficient amount of water is available for infiltration. So this is called potential infiltration. But what is ponding time? It is nothing but the time elapsed between the when the rainfall begins and the time when water starts ponding, right? Then we derive equation between equation of ponding time. So equation of ponding time, this is the equation of ponding time, and this is the equation of infiltration after ponding time. So we have seen numerical based on ponding time method. Then we came into fourth module, that was about surface water. So we started with introduction, then we talked into first atmospheric water. There we have covered three variables, that were precipitation, evaporation, evapotranspiration. Then we started exploring subsurface water, where we learned about another important variable called infiltration, another important process called infiltration. Now we are talking about surface water. So here we are going to talk about runoff. So first we started with the definition of runoff, then what are the different techniques, how we can estimate a rainfall. So rainfall hydrograph or excess runoff hydrograph, that is phi index, runoff coefficient, infiltration equation, and SCS curve number method, right? So we have explained, we have talked in much detail about SCS curve number method. We have seen numerical based on SCS curve number method. Then we have seen like how we can measure surface water. So there were different techniques. So first was stage measurement technique, where we have talked about non-recording and recording stream gauges. Then we talked about velocity measurement technique. In here we have explored current meter in detail, and we have looked into ADCP and ADVP. Then we have seen like stream flow could be measured, direct measurement also. So in direct measurement we have covered area velocity method, moving boat method, dilution technique, ultrasonic method. And we have seen numerical on area velocity, moving boat, and dilution technique. Then we continued with the same module, and we started exploring like what are the different types of hydrological models. So based on these three functions, these three parameters, that is space, time, and randomness, we can derive different types of hydrological models. So if any model is a function of space or is a function of randomness, we can divide those model as deterministic or stochastic. So deterministic is the model which ignores randomness, and stochastic is the model which consider randomness. Similarly, if any model is ignoring space or any model is considering space, we can divide those model also, right? And with respect to time also. Then we have seen like how all the hydrologic system models are based on linear system. And when we talked about linear system, we have talked much in detail about two principles, that is principle of proportionality and principle of superposition. Then we have learned about input and response function of linear system. So there are three types of input of linear system, that is unit impulse, unit step, and unit pulse, right? And corresponding the response functions are also there. Then we have learned about this very important equation called convolution integral equation. Then we have seen the relationship between different response function. Then we started exploring hydrograph, right? So hydrograph are what? It is nothing but a graphical. A hydrograph is nothing but a plot between discharge and time. Here we talked about much more into unit hydrograph. So you should remember the definition of unit hydrograph, which is it is a DRH resulting from one axis of 1 centimeter of excess rainfall generated uniformly over the drainage area at a constant rate for an effective duration of dr. So here we talked about how we can derive unit hydrograph, right? So there were certain steps how you can derive unit hydrograph. We have seen that. Then we talked about S hydrograph and instantaneous unit hydrograph. So you should remember the definition of S hydrograph and instantaneous unit hydrograph also. So S hydrograph is, it could be obtained by summing of the ordinate of dr unit hydrograph, and instantaneous unit hydrograph is similar to unit hydrograph. The only thing changes is instead of rainfall of 1 centimeter, it uses rainfall intensity of 1 centimeter by dr duration. Then we talked about synthetic unit hydrograph. So the important application of synthetic unit hydrograph is in place where we don't have gauging location. Like if there is some catchment and we don't have any proper instrument to measure the stream flow there, so in that place we can use synthetic unit hydrograph, right? Then we started exploring flow routing technique. So flow routing technique was other divided into hydrologic routing and hydraulic routing. So in hydrologic routing we studied about lump flow routing technique, and hydraulic routing is called distributed flow routing technique. So in flood routing we have mostly talked about hydrologic routing. So hydrologic routing is further classified into reservoir and channel, right? So in reservoir channel we have studied one important method called modified spooled method. So I would suggest to go and revise the numerical based on modified pools method. And similarly for river routing, another important approach was Muskingum method. So the numerical for based on modified pool and Muskingum method are important for examination point of view. Then we started exploring the sixth module, which was all about probability, right? So here we talked about what are the different types of processes and what is random processes. So we know like all the hydrological variables are random. Random means it can take any value within certain range. Then the random variables were further divided into two types, that is discrete and continuous, right? So discrete means it would have some certain finite value, whereas continuous value, random variable could be in a particular range. Then here we talked about probability distribution. So probability distribution will give us the relationship between the random variable and their corresponding probability value, right? Then we have revised the basics of statistics by use of measure of central tendency, measure of dispersion, symmetric and pickiness. So we have revised. Then we talked about what are the different types of probability distributions that are used for different hydrological variables. So when we talked about discrete probability distribution, we have talked about binomial and Poisson distribution. And when we talked about continuous probability distribution, we have covered exponential, gamma, normal and Gumbel. And we have seen numerical based on Gumbel distribution. Then comes the most important topic from this module, that is frequency analysis, right? So frequency analysis, it is nothing. Frequency analysis will give the relationship between the magnitude of extreme events to their frequency of occurrence through a probability distribution, right? Then we have seen the relationship between return period and probability of exceedance. Then we have seen how we can analyze frequency analysis, right? So there are two ways. The first way is by using probability plotting, and the other approach was using Gumbel. So we have seen numerical based on both the method. Then we started with the last module of the syllabus, that was on hydrologic design. So here we talked about hydrologic design scale and hydrologic design label, right? Then we talked about two important relationships, that is maximum depth duration curve and intensity duration frequency relationship, that is IDF and DAD. Then we talked about design flood, like how in order to design flood there are two approaches. The first approach is probable maximum flood. So in probable maximum flood we can use rational method, or we can use empirical method, or we can use flood frequency analysis. Then these are few of the numericals that we have seen over the period of the course. Then this is the numerical from second module, that is atmospheric water. So here we talked about, we have studied 5 important definitions, right? We have studied about vapor pressure, relative humidity, saturated vapor pressure. So this is a numerical based on that. So if we recall the definition of each of the variable and the numericals and the relationship between them, it is easy to understand this numerical, right? So here they are saying like how the altitude is varying, so how the different variables will vary. Like if at depth of 0 meter there would be some temperature, there would be some dew point temperature, there would be some relative humidity, how it is going to change with the change in altitude. So this kind of numerical we have seen in the class, right? Then we have seen numerical based on how to calculate amount of precipitable water, right? So this equation, we have to remember the equation to calculate the amount of precipitable water. So that equation is QV average into rho A average into area multiplied by delta Z. So the important thing here to calculate is QV average and rho A average. QV average means specific humidity average. That means we have to calculate specific humidity at both the depth, that is at ground surface, and then at the corresponding height that they have given, right? And similarly we have to calculate density of air also at ground and also at corresponding height, and then we have to take the average of it. Area is given to us, delta Z is given to us, then we can multiply and get the amount of precipitable water in kg. Right, then we talked, then we have seen numerical on another important variable called evaporation, right? So in evaporation we have studied three methods, that is energy balance method. So the equation for energy balance method is nothing but Rn upon Lv rho W, where Rn is net radiation, Lv is latent heat of evaporation, and rho W is density of water. So if we recall this equation, the important thing here to calculate is latent heat of vaporization. So the equation for that is here. If we recall this equation, if you remember this equation, it is quite easy. It is to solve energy balance method, and the equation is also not that tedious. Then we have talked about aerodynamic method, right? So the equation for aerodynamic method is quite tedious, so we have to remember this equation, and then we can calculate aerodynamic method. And when we combine these two methods, then we can get third method called combined method. Then we have seen numerical based on how to calculate evapotranspiration. So here we have seen numerical based on Penman's formula, right? So the Penman's formula is here. This is the equation for Penman's formula. So here we need to calculate it. It's like three terms. First time is to calculate delta. So what is delta? Delta is nothing but the slope of saturation vapor pressure, right? So that we can calculate by the equation of dES by dt. Then we have to calculate EA. So EA is nothing but it is the parameter which includes saturated deficit and wind velocity. That is ES and EA. This is nothing but saturation deficit, and U2 is nothing but the velocity at 2 meters above ground. Then another thing is psi. Psi is nothing but, gamma is nothing but psychometric constant which is given to us, and the last important thing is to calculate net radiation. So in order to calculate net radiation, we have to use this equation. So we have seen this numerical. I would suggest to once do practice this equation, this kind of numerical, because they have quite a long equation. Then we talked about infiltration. In infiltration we have studied ponding time, and we have seen numerical based on ponding time concept. So how to calculate ponding time TP, and based on that how we can calculate cumulative infiltration, right? So there is a relationship between TP and FP. So that relationship is here, nothing but you just have to multiply it with intensity of rainfall, and then you can get FP. So that kind of numerical we have seen. Then this is module 5, where we have seen how we can calculate the discharge. So there are different methods. The first method was using velocity, that is using current meter. So you just have to calculate the value of velocity, and based on that you can calculate discharge. Then there was another formula for average area velocity, like if there is difference in depth, so how we can calculate, right? So this kind of numericals are very easy. This could be asked for 1 or 2 marks in examination. So we have to remember like 1-point method, 2-point method approach that we have seen in the class. Then the important numerical was area velocity approach, where we have seen the calculation, how we have to take the average width and multiply with the depth, and then we'll get the area, and then we can multiply that area with the velocity value which is given to us. So area into velocity will give you the corresponding discharge for each section, and then you can take the total of that and you can get the overall discharge. Then we have seen moving boat approach. So moving boat approach and area velocity approach are similar to solve. Then we have seen next module of hydrograph. So here we have seen how we can derive hydrograph using rainfall and stream flow data, right? So we have stream flow data with us. So here in the stream flow data, what the first thing is to separate the base flow. So in this particular question, the first important thing is to find the base flow, right? So if you can see, for the corresponding time 6 hour, the stream flow is 12, and again the 12 value is repeating after 48 hour. So if we can line these two joint, because we know there are different techniques to separate the base flow, straight line approach, variable slope approach, right? So we are using straight line approach here, and we are eliminating all the values that is coming below 12. So these three values will be eliminated. So we can say all the values above this are nothing but they don't have any base flow in them. So the first thing is to separate base flow. So when we separate base flow from a stream flow, we get is direct runoff, right? So we calculate direct runoff here, and based on direct runoff, now you can calculate the ordinates of unit hydrograph. We know the relationship between how we can calculate ordinate of unit hydrograph is direct runoff divided by the excess rainfall, right? ER value. So here we have calculated the ER value, which is 7. So if you divide 7 with the direct runoff ordinate, we will get the corresponding unit hydrograph ordinate. So this kind of numerical we have seen. Then we came to the sixth module, where we have learned example, when we have seen example on frequency analysis, right? So in frequency analysis, we talk more on two approach, that is Gumbel approach, and another one was probability, right? Probability plotting. So this is the case where we are using probability plotting. So here generally what we do is, we have the rainfall series with us, we just have to arrange them in the descending order, and then according to that we will give them the rank. So the highest value will be having rank 1. Then there is another approach, like different probability approach methods to calculate probability. So here we have used Weibull approach, the formula for which was m upon n plus 1, where m is nothing but the rank assigned and n is the number of observation plus 1. So this will give us probability, and we know the relationship between probability and return period. Return period is nothing but 1 by p. So accordingly we will get the return period. Now what we can do is, we can plot the relationship between an annual rainfall and return period, and with the help of that we can get the value of like if we want to get what would be the return rainfall value for a particular return period, let us say return period of 50 or 75. So what is the return annual rainfall value corresponding to return period of 75? So it would be something between 200 to 250. So this kind of work we have, this is the application of frequency analysis. Then we have seen the last model, which was based on probability, right? So we have seen numerical on binomial distribution, and with the help of which we can estimate the probability that a flood will return after a return period of 100 years, right? Then we have seen the application of Gumbel distribution also. Then we talked about, then we have seen some example to calculate risk, like what would be the risk. So in this example they are saying the design life of a structure is 100 years. Estimate the risk involved for this hydraulic structure if it's designed for 50-year return period flood and a 200-year return period flood. So we want to calculate the risk. So we know that risk is nothing but 1 minus non-occurrence probability in n number of years. So the n year is the design line of structure, that is 100, and t is nothing but the return period. So we are going to design it for 2 return periods. So for first case the t would be 50, and for second case 2 would be 200. And similar kind of numerical we have seen for some different example. Here we are going to design the culvert for a return period of 50 years whose design line is of 5 years. So these are all the numericals that we have seen throughout the syllabus or throughout the coursework. Now what I would suggest is to revise each and every numerical and each and every concept before your exam, and also do practice all the assignments which were given to us. So we have also discussed the assignment while we were doing the live session for each of the module, and also if you want to revise few topics or few concepts, so you can go and check the videos that has been the links which have been shared to you, and you can go and revise that particular concept or particular numerical before your examination, right? So I hope this course was quite interesting and quite learning. So I hope I gave a quick summary of the entire course, and now you can accordingly plan for your exam. Like, you can develop your own strategy and how you can going to attempt. So the more you practice, it would be more helpful for you, because there are few numericals where you have to remember the equation. So I would suggest to go and practice those kind of numericals. And also I'll be sharing all the slides, like all the summary slides and all the numerical slides, all the important numericals that I think that could be. So I'll be sharing this in the Google Drive link after the lecture, so you can access them through that also. I think numericals on flood routings are left. We'll revise few numericals on flood routing. Like we have seen this numerical on how to calculate the drainage area, right? So here what we are going to use concept is triangular unit hydrograph. So in case of triangular unit hydrograph, we are going to calculate the area within the triangle, right? So here what you are going to do is, firstly, if you want to calculate the runoff volume, what you are going to do, you are going to calculate the area under unit hydrograph. So the area under unit hydrograph would be half into base into height. So here the base would be the time base and height would be the peak discharge. So in the given question, they have given us the peak discharge as 28 and they have given us the base as 16 hours. So we are going to convert 16 hours into second, which give us 57600, and 28 is the peak discharge. So if we calculate the area, we get the rainfall runoff volume. The next step is to calculate the area. So we know the rainfall volume is equals to ER into area. So we want to calculate excess rainfall. So this is a case of unit hydrograph. So excess rainfall would be 1 centimeter, and we can get the value of area. Now there is another important numerical on derivation of direct runoff hydrograph. So we have time and we have corresponding unit hydrograph. They are asking us to derive direct runoff hydrograph, right? With ER of 2 centimeter and 3 centimeter occurring in two successive 3-hour duration. So firstly, what we are going to do is we are going to calculate the DRS due to 2-hour due to excess rainfall of 2 centimeters. So how we can get that? We can just simply multiply with unit hydrograph ordinate value. So 10 into 220. Similarly, we can get the entire series. Now they are saying due to 3 centimeter, right? So how we can do is just we have to take a they are saying there is a gap of 3-hour duration. So we have to start with 3-hour duration. So for 3-hour duration, it would be 0. Then the next value comes 10. So there is a lag of 3 hours. That's why 3 into 10, it is coming 30 here, because there is a lag of 3 hours. And now what we are going to do is we are going to combine them. So just we are going to add the last two column and we are getting combined DRH. And here is the plot for each of them. So the first plot is for unit hydrograph, that is light blue. Then for direct runoff due to 2 hours, 2 centimeter is in green color, then in 3 color, and then so when we analyze this thing, we know that how the peak is increasing and how the time base is also, and there is also a lag when we see, right? Then we have seen numerical on flood routing and flow routing also. So we can revise those numerical based on flow routing and flood routing. Let us see numerical and combined method, because this is one of the lengthiest of numerical. As you can see, the entire question data set is quite large. So we just have to stick to the basic, like first thing is we need to calculate an evaporation based on energy balance. So the equation for that is ER is equals to RA LV by rho W. So now we can calculate LV, for which we need only the value of temperature. So if we know the value of temperature in degrees Celsius, which is 14, we can calculate latent heat of vaporization, and by using LV we can calculate ER value, right? Now the next thing is to calculate EA, that is evaporation using aerodynamic method, for which we know B into ES minus EA. So ES and EA value is given to us. The important thing is to calculate this constant value of B. So the equation for B is quite large, right? So we have to calculate this B value, and then we can get the value of EA. Now that we know the value of ER and EA, we can go for combined method equation. So here again we need to calculate two things, that is delta and gamma. So in most of the cases gamma would be given to you. If not, then again you have to remember the equation for psychometric constant, that is gamma is equals to Cp into P upon 0.622 Lv upon Kh into Kw, and this will give you the value of psychometric constant. And delta is very easy to calculate. We know the equation 4098 Es upon 237.3 plus T the whole square. The important thing to remember here is 237.3. Most of the time we get confused with 273. Right? Now that we have calculated each of the variable, we can go and simply substitute here in this equation, and we can get the value of evaporation. Similarly, just go and revise this method also, Penman method, because the numericals, like the equations, are quite large. Then the numerical based on two important method of flood routing, that is modified Puls and Muskingum method. So I would suggest to revise these two method, because the numerical on these two methods are quite lengthy. So I would ask you, like I would request you to just practice this equation, these two method, that is modified Puls method and Muskingum method. So we'll revise one equation like numerical on Muskingum method, right? So here the first, in the first method they are saying like determination of Muskingum coefficient. So we need to find the coefficient of Muskingum, that is C1, C2 and C3, right? So in order to find C1, C2, C3, we need to get the value of K and X, right? If you look at the equation of Muskingum equation, K equals to K into Xi plus 1 minus X of Q. So here the coefficient of Muskingum are K and X, where I and Q are the input and output. So inflow and outflow are given to us. We are required to find the value of K and X. So how we are going to start is, firstly we are going to calculate the difference between I and Q. We are going to calculate the value of delta S, right? Then when we know the value of S, now what we are going to do is we are going to assume the value of X, because we know the value of X lies between 0.1 to 0.5. So here we have taken the X value as 0.2, 0.3, 0.4 and 0.5. And with this value of X value, we will get certain values, right? We are going to substitute this X value in this above equation, because we know the value of I, we know the value of Q, then we can get this term Xi plus 1 minus X of Q, right? Now what we are going to do is we are going to plot them, and we are going to look for that value would represent a straight line. So if we know that where X is equals to 0.4, the line is a straight line. So what we are going to do is we are going to take the slope of this, and that slope value would be nothing but K. So the slope value is coming to be 12.05 hours. So here we can calculate like for this particular data set, the value of X is 0.4 and the storage constant value is 12.05. Then another numerical that could be asked for Muskingum method is to calculate the attenuation and peak, right? So here they have given the value of X and they have given the value of K. So the first thing is to calculate the coefficients, right? That is C1, C2 and C3. So we know the equation for each of the Muskingum coefficient, which is based on time and K and X. So using that we got the value of C1, C2, C3. Now we are going to prepare a table whose first and second column would be the data set that is given to us. The third column would be C1 into I2, because this is the equation to calculate the discharge for second time period. So we have to prepare a column for this, prepare a column for this, and prepare a column for this, and when we add the three of the column, we'll get the outflow discharge, right? So using the same method for the first initial output, the same would be the outflow, and for this, now this will be the inflow for the next value, and we have to calculate the value of outflow. So this is nothing but this is Q1. So we are going to multiply C3 into Q1. It means 0.687 into 152 will give us this value. C2 into I1. So I1 is what? I1 is the inflow. So inflow is nothing but 192. So 0.25 into 192, and similarly 0.0625 into I2 is 192, right? And then we can add this three term and we can get the value of outflow discharge. And same approach we can use. And lastly, we are going to find the attenuation. Like similarly, when for the inflow the maximum peak was 475, and for the outflow maximum peak was 402. So if you are talking about the attenuation, it is nothing but difference in peak, right? So here the difference in peak is 475 minus 402, which is coming 72.27. And similarly, if you can see the delay, so the time delay is when the inflow is 475, the peak is 475, and in order to this peak to get reduced, it is taking almost 2 days. So the delay in time is nothing but 2 days. So this kind of numerical could be asked in examinations. So I would suggest to revise both of them, Muskingum coefficient, Muskingum method, as well as modified Pull's method. So I think we have covered almost everything. I wish you all the best for your examination.